A wave is a field, meaning a wave is defined, has a defined value everywhere in space. And if you look at the wave, this is a wave. And this one is like extending in both directions infinitely. It covers all the space. Space. So it has this, here is value, and this is a position. And these positions are the space. In this case, it's a one-dimensional space, but it can be two-dimensional, like a sheet, or it can be three-dimensional, or any dimension. 1D, 2D, 3D, doesn't matter, but it has value everywhere. So in this sheet it says value everywhere, and in this volume it has a value everywhere in the volume. It covers the entire space, because this is how a wave looks like. It goes indefinitely all over the place. It's important to notice that this value here is not something that if you look at the one-dimensional case, it's not something that extends outside the space. This is just a visualization of those values in this field. Now, those values happens to be, like if you look here, at a certain lowest level here, and a certain highest level here, lowest, and then it goes higher, and then the value gets lower, and then it gets higher, and lower, and higher. And the way those values is spread out in that space forms a wave, which we could visualize like this. So this is one dimension. This line here is positions, and this is the value in each of these positions here. So here, at this position, it has this value. At this position, it has another value. Okay? But it doesn't extend out here. There is nothing that goes out here. It's a value in that position. So you could think about it like stronger values and thinner values, but for us to be able to have a visual representation of this, I'm doing a two-dimensional representation of it, but there is nothing two-dimensional with this. It's just values here. Okay? So this is a wave, and it's defined all over all space, which means a wave is a field. Now, there is interesting things with waves. You can sum them up. So let's say you have a wave like this, and it just continues. And then you have another wave, like this. You could sum them up, and when you're summing them up, you may get something looking like this. Okay. Then it goes down like that, and up here. The point I want to make is that the combined wave here this wave here, first of all, its shapes is not the same as the combined waves. These waves here are pure waves. It's just one frequency in that wave. When you combine waves of different wavelengths or frequencies, you get a combined wave which has another shape, not necessarily the same as the one you had before. You can have if you combine if you combine two waves like this that is very close to each other, they will kind of be the same, but they will be higher values, because you add them up. This is summation of two waves, and the summation of waves is quite interesting, because you can define a 0 point here, and then you can have two waves that are mirror image of each other at the 0 line. So since this is 0, it means it's negative here and it's positive here. So this has negative values here. The wave here is negative values underneath here. So whenever the wave goes here, it has a negative value, and whenever it goes above the 0 line, it has a positive value. And since they mirror image of each other, it means that the combined wave will be a straight line with 0 values all over the place. So another way to say that is that the combined wave, if you're combining two waves, you can make the wave disappear. But it is important to understand that the values of this wave is still defined all over the place here. It's namely 0 at every spot. But it's still a wave there, because it's a combination of two waves that cancel out each other to 0. So everywhere in space, the value of the wave is 0. The next concept is that of a wave package. What is a wave package? Well, a wave package is it's a wave that is 0, and then it starts to have the small waves, and then it comes bigger waves, and even bigger waves, and then it goes back to smaller waves like this, and then it's 0. Notice this shape here. This thing is an envelope of the wave, and what I mean with the envelope is that it has those points here where if you are on this side, let's say the outside of that envelope, the value of the wave is 0, and inside here it's non-zero. Well, it can be 0. Here it's 0, it's 0 here, here. Every time it passes 0 line, it's 0, but it has a non-zero value as well. Here, 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 here is the non-zero value. So inside the envelope, the package, you have non-zero values. Outside the package, it's a 0 values. And the reason it can be 0 is that you can combine waves in such a smart way that at a certain region in space, so these are still here, these are positions, you could combine several waves in such a way that you get a package like this. Now, these are positions, and this is basically fixed in space, so this stands in a fixed position, but you can make this move by adding a time component to the wave. You make it time dependent. The thing here to notice now is that this is a combination of waves. So if I have this wave package, and here is an envelope of that wave package, that's the base wave, which extends to infinity. I should only do this, forget this curve. So this is wave package here. So you have the base wave here. Which extends to infinity. And then inside you have smaller waves, like this, that also extends to infinity. And not just remember now, this is a lot of waves inside here, and the shorter the wave is, the smaller it is, but they are combined in such a way that they create this package. It's possible to do. You have to trust me on this, because I'm not going to show it how it's done, but this is a case. And the issue here now is that when you move waves, that these bigger ones, they will move big or long, they will move slow. Shorter ones, and the shorter they are, they will move faster. Short will move fast. That means that means if you change the relative position of this carefully organized wave package, like this, so you have at one time point here, you have them lined up in a certain way to create that wave package. Then in another time point, so it's here at this position, then it has moved over here. That means that this big wave, since it's moving slower, the peak of this, the smaller one has moved out of phase with the big one, so they're not overlapping in the same way anymore. And if you look at where that envelope starts and ends here, they come out of phase with each other, and when you sum them up, they will not be zero, but they will kind of like extending out at the sides like this. That means that over time, when a wave package has a certain space like this, and over time, as it moves, it will start to, that blob will start to smear out. So what we're talking about is like here it has a position. Let's say it's at position 1 here, and then it moves over to position 10, and while it moves here, it smears out. And notice you have the center line here. It smears out in the frontal direction and backwards direction. And this has to do with that the different waves are moving, the different components of the wave package is moving at different speeds. And I have to stop here now.